So the title of the report is Inversion of the two data spherical radon transform using local data. The problem has a history. It is known that the base of computed tomography is the classical radon transform, and the mathematical base of the radon transform is the classical mathematical. So the mathematical base of the computed tomography is the classical radon transform that maps a function to its integrals over straight lines on the plane. You see the transform, but there is a hook problem. It turns out that during the single slice CT exam, a patient receives a radiation dose that is equivalent to what an average person might receive in 10 years from background radiation. In today's 3D and 2D tomographic reconstruction, approximately 60 slices are needed. So now researchers using various types of, say, physical signals have developed new methods for tomography. The thermoacoustic tomography, TAT, is the most successful. The base of thermoacoustic tomography is thus already spherical radon transform that maps a function to its integral of spheres with the center detector locations. First, about the spherical mean. So by SPT, we denote the sphere with center P and radius T. So for a continuous function, we consider the restriction of the function onto the sphere. So the point P plus T omega, omega is the spatial direction, belongs to the sphere, and we integrate the restriction of the function over the sphere with norm Lebesgue measure. So this is a mean, spherical mean. So by definition, the spherical radon transform, SRT, takes function f to its spherical means, where the centers belong to some subset, which is a hypersurface, and T changes from 0 to infinity. So this is a spherical radon transform. Definition: a set L is said to be an injectivity set if the data collected by the detectors along L are sufficient for unique reconstruction of F. There are many mathematical problems here, but from my point of view, the main mathematical problems are finding the sets of injectivity of SRT and reconstruction of unknown function from SRT. In other words, to invert spherical radon transform. The inversion of SRT is required in mathematical models of thermoacoustic tomography, photoacoustic tomography, in radar imaging, and of course, are theoretically important in many areas of mathematics. So, no results. Professor Agnarowski and Quinto have given a complex characterization of the set of injectivity of SRT on the plane. As I know, for free and high dimension, the problem is still open. And also, the main result here, also from my point of view, is the following. Belongs to many authors. A function supported within a convex body is a compact subset, can be uniquely recovered from its spherical means, where the centers are located on the boundary of the body. So for several geometries of detectors, exact inversion formulas, as usual, the back projection type formulas for the spherical radon transform are known. There is a vast literature on the topic. Let me introduce some of them. Of course, Mark Agranovsky, Kuchman, Kunyansky, on reconstruction algorithm for the SRT, inverse problems. Kunyansky, also inverse problems. Heltmeyer, Nguyen, iterative methods for photoacoustic tomography. Finch and Rakesh, recovering a function from its spherical mean values into 3 dimension. In this case, the centers located on a line and on a plane, respectively. Siam journals, meta-analysis. Heltmeyer, universal inversion formula, Siam journal. Also Agranovsky, Kunyansky, on the existence of universal back projection formula for spherical means, radon transform, inverse problems. Of course, Netterer, photoacoustic inversion, convex domain inverse problems and imaging, Nguyen. And let me introduce two of my articles on this topic. In these articles, a new approach, which I called the consistency method, was suggested to invert the spherical radon transforms. These formulas allow us to reconstruct in two-dimensional case, of course, when in the first article the centers belongs located on a line. On the second article, the centers belong on the plane. In 2D, in three-dimensional cases, using this formula, one can these formulas allows us to reconstruct unknown function using local data. So both formulas have the benefit of being local. I will come back to this later. So maybe it is most interesting for you. Note that the problem of reconstruction of a function from the spherical means is known to be equivalent via Kirchhoff-Poisson formula to the following boundary variable problem for the wave equation. You see the wave equation. Here, O is the induced pressure wave, F is the initial pressure, and the problem is to find the X from the Dirichlet data. That is the solution of the wave equation on L 0 infinity. I did not use this relation. So note that, as usual in literature, the injectivity of SRT for compactly supported function is considered, and the situation becomes more complicated without the compactness of support condition. The assumption that the support of F is compact becomes crucial for the proof of in both cases, in the integral equation and the wave equation. I took these sentences from this review, Kuchman-Kunyansky. Now about the problem. It is clear that a hyperplane is a set of non-injectivity of SRT in the space of continuous functions. Now we are in r-dimensional space. Because really one cannot recover a node function f with respect to a hyperplane on odd function with respect to our hyperplane using spherical means with centers located on the hyperplane, because we have no signal. And the problem arises. Find an additional condition that allows us to use to reconstruct unknown function. Now we are in three-dimensional case, not necessarily with compact support, using SRT with detectors placed on a plane. And this problem is proved to be equivalent to the injectivity of the so-called two-data spherical radon transform. By the way, the problem was already solved and printed in these two articles in two-dimensional case. In first article, inversion of the pair of weighted and classical circular radon transform in the plane, journal mathematics application, and in the second article, reconstruction function from circular integrals centered on an arc, journal mathematical sciences. And now I will represent the solution for three-dimensional case. For this, I consider the following transform. We consider the center of spheres belong to the xy plane for simplicity. The point PQ0 is identified with PQ, and I consider the following transform. For a continuous function, f, also as in previous case, I consider the restriction of the function onto the sphere SP with center P and radius T, and now I integrate with some weight, which is a complex value function, and integrate over usual spherical measure. So this transform consists of two parts. The first part, the real part, is the classical spherical radon transform, and the imaginary part is the spherical radon transform with weight cosine phi. Here, cosine theta. Here, theta phi is the usual spherical coordinates of spatial direction omega. Theta is just the polar angle measured from z-axis. Here you see the picture. The main results. The theorem states that let there be a planar domain, an open subset on xy plane, when the transform to data spherical radon transform, where P, the centers belong to D, is invertible in this subspace. To understand, to explain the meaning of the parts, we consider so one can reconstruct unknown function f using the data on the data of the detectors belongs to D. To explain the meaning of the parts, let me to denote the restriction of f onto the plane, onto the sphere PT by this way. And I consider the spherical harmonic expansion I write as follows, of the restriction as follows. Here both AMM and BMN are the Fourier coefficients, and Pn Legendre polynomials, Pnm associated Legendre polynomial, as we know here. So M, the spherical mean is the first element, A00, and for the second coefficient, A01, we obtain, which is these integrals, and of course it is integral f cosine theta, because P1 cosine theta is cosine theta. So hence, for the real part and for the imaginary part of the transform, which I consider, we have real part is the spherical mean, and the imaginary part is the Fourier first coefficient of the restriction of f onto the sphere SPQ tab. Thus, theorem 1 states to recover unknown function, note that the support can be non-compact. It is sufficient to have the Fourier first two coefficients, MF and A01 of the restriction of f onto sphere where PQ belongs to D. PQ0 belongs to D. Okay? Now about inversion formula. Reconstruction formula using Fourier coefficients. For a point xyz, I consider the sphere with center xy0 and radius z. Of course, the point belongs to the sphere, and for the polar coordinates of the point with respect to the center, we have substituting this expression into the expansion formula, we obtain the following formula, reconstruction formula, one can say, for the unknown function. Fxyz is the sum of the following series, where A01 are the Fourier coefficients. Okay. Also considering the case where the point, for the point where z less than 0, we get finally the following theorem. Fxyz is the sum of the series. Here sigma is the usual sigma function just. Okay. Thus, the problem of reconstruction of f from the mean value and the Fourier cosine coefficient A01 is reduced to finding the coefficient A0n. Note that in that article, inverse probability imaging, to find the inversion formula for the SRT, for a function supported on one side of plane, we needed to find coefficient with even parameters, numbers. To find this coefficient, I apply the consistency method. Very short about the method. For a point xyz, we consider the bundle of spheres where the centers belongs to xy plane containing the point. And the consistency method is based on the following statement. When we consider the restrictions, they are consistent. We mean the following. The values of these restrictions at the point xyz are the same. Okay? So, hence, 12 does not depend on P and Q, on the center. Now about the inversion formula. We derived the unknown coefficient from the derivation of the Fourier coefficient. Using the method, we found a free system of partial differential equations on the coefficient A01, which we solved recursively. Let me represent that one of them. You see that to obtain A0n, the coefficient A0n, we need also coefficients A1n and B1n, for which I obtained also two other systems of differential equations. And finally, we expressed all Fourier coefficients A0n at the point P, Q, T in terms of the mean values f and the Fourier first cosine coefficient A01 of the restriction of f onto the sphere S, P, Q, T. Now about the inversion formula. To formulate or to write the inversion formula, we construct two sequences of standard polynomials. You see the polynomials defined on the segment 0, 1 of corresponding degree, of course, and we suggest an algorithm to calculate the coefficient Cn. I call them standard because their construction does not depend on f. So they're like Legendre polynomials, okay? So we have two sequences, we define two sequences of standard polynomials. And now about the inversion formula. For a given smooth function, let MF and A01 be the MF be the spherical mean and A01 be the Fourier first coefficient of the restriction of f onto the sphere SPT. When we have the following theorem, fxyz, this is inversion formula, fxyz is the sum of the integral of this function. You see, to recover the value of f at the point xyz, we use just the data of detectors at the point xy0, and u changes from 0 to module z. Here you see the Laplace operator, and then multiply with that polynomials, integrate, and consider the sum. So to reconstruct the value at the point xyz, we need just the data from detectors replaced on a neighborhood of a point xy0. From this, it follows from the theorem for reconstructing f xyz at any point xyz, we use the local data of mf and a01. So let f be a smooth function. To restore the value of f at the point xyz for any point, we use the values of mf and a01 over spheres with centers pq0 belongs to U, where U is a neighborhood of a point x of the projection point. Okay, of the projection point. Now let me show a computational implementation. So let me consider this function, which is a bad function, bad case from a spherical Radon transform point of view, SRT point of view, because this is an odd function, okay? And you see the plot of the function. More precisely, we consider the restriction of function onto the plane because function depends on free variables. On the plane, y equals 3, and you see the plot of the function on this rectangle. Now I try to reconstruct this function, more precisely, approximate this function by the formula. So I calculate by hand mf, which is 0 because the function is odd, and a01 has the following expression. I also calculate the polynomials, after substitution into the formula, into the inversion formula, you see the plot of the approximation of the function. It is very close to previous plot, but not the same. Okay. Now about the classical spherical Radon transform. It turns out that using the inversion formula, one can find an inversion formula for the classical spherical radon transform for the function supported on one side of a plane, not necessarily with compact support. Indeed, if you have some function, smooth function fc, we defined supported in half space z greater than 0, we consider the even function which coincides with the function fc on this half space. You see this function. It is clear that for the Fourier first cosine coefficient of the restriction onto the sphere S, X, Y, T, we have 0 because it is even function. Hence, f as well as fc, our function, can be restored from its SRT of a sphere centered on the xy plane. Okay, let me show the inversion formula. So, if f be a smooth function defined in three-dimensional space and supported on one side of xy plane, also the support can be non-compact, we have the following expression for the fxy. So fxyz is the sum of the following integral. Here also we consider the data from the projection point of xyz, and u change from 0 to z. Also delta is the Laplace operator in 2 dimensions with respect to x and y. Multiply with the polynomials and integrate. And finally, we obtain this function, restore the function. So you see that this formula has the benefit of being local. I mean the following. For a fixed x, y, z, to restore the value f at the point, we need the values of mf, spherical means, with the centers in a neighborhood of projection point, and T changes from 0 to z. Note that the well-known back projection type inversion formulas for recovering f(x, y, z) at any point uses the data from all the detectors on the plane. Let me explain maybe. So, for example, if we have some functions of free variables and we would like f and we would like to recover the value of the function at point x, y, z, we need just the data from the projection. We need that data from the neighborhood of the projection detectors, because we consider the Laplace operator. So using this data by this formula allows us to recover the value of the point. If we have some function with compact support, just by data from the projection data, one can recover the function. Using back projection type formula, to recover the function, you need the data from all plane. So let me explain. Also, I have some computational implementation. So we see, we consider the function for z greater than 0, and you see the plot of the function. The restriction of the function onto because it's a function of free variables, onto the plane. Do you see the plot of the restriction of the function on the rectangle? And using, I try to approximate this function by using the formula. I calculate the spherical means, which are the following expression, and you see the plot of the approximation just on first step. Of the approximation of the function, which is also very close to original plot, but there are a little difference. Okay, so thank you for your attention.